Now let us try to prove the correctness of Huffman coding. As we said at the beginning, there are two things we have to prove to ensure that the algorithm is correct. First of all, does it have the greedy property, and is the greedy property safe? And then second, does it have the optimal substructure? If we can prove these two, then definitely the Huffman code algorithm is a correct greedy algorithm. So we're going to prove this as two lemmas. The first lemma is about the greedy property. So consider two characters, x and y, with the lowest frequencies. Then there is an optimal tree in which x and y are siblings at the deepest level of the tree. Remember, we said the greedy property of the Huffman is that it is trying to put those characters with the least frequency at the deepest level. So this lemma is saying, well, that if we follow through with this idea, we will have an optimal tree. That is, consider two characters x and y with the lowest frequency. Then there is an optimal tree in which x and y are siblings at the deepest level of the tree. Okay, so this is what we're going to prove. Proof. Let T be an arbitrary optimal tree. Okay, optimal prefix code tree. And let A and B be two siblings at the deepest level of T. Okay, so we have an optimal tree, but at its deepest level, we have two elements, A and B. Okay, we're going to try and show that if we replace this A and B with this X and Y that have the lowest frequency, then the tree will remain optimal. This is the idea. Okay, we will show that we can convert our optimal tree T here to another prefix tree where X and Y are siblings at the deepest level, but without increasing the cost of the tree itself. If we can do that, then the lemma will be true, that there is an optimal tree in which X and Y are siblings at the deepest level. Okay, so we start with a tree that is optimal, but at its deepest are not X and Y in the sibling in the deepest tree, but A and B. So we're going to show that if we replace A and B with X and Y, it will still remain optimal. And that is the way we're going to prove the lemma. Okay, so we're going to switch A with X and then switch B with Y. Okay, as you can see in this tree. So suppose this is our optimal tree T, where as you can see A and B are at the deepest and Y and X are somewhere in the top. So we're going to try and switch first A by X. So instead of A here, we will have X, and instead of X here, we will have A. This is step number one. And then in the second step, we will switch the Y and B. So instead of Y here, we will have a B, and instead of B here, we will have X. So we're going to have a tree with X and Y being the one in the deepest level. Okay, of course, X and Y has the least frequencies. We said this is the proposition, and that this tree is still optimal, just like T. So if we can do that, then we will have proved the lemma. Okay, so let's go ahead and do that. First of all, we're going to make some assumption which will not create any problem with the theory or with the lemma. Without loss of generality, we're going to assume that the frequency of x is less than or equal to the frequency of y, and that the frequency of A is less than or equal to the frequency of B. Okay, if you swap, the algorithm will still work, but just to make things easier, without losing generality, we're going to assume we know that x and y are the least frequent elements. So suppose, definitely one of them is going to be lower than the other, or maybe they will be equal. So let us say the frequency of x is less than or equal to the frequency of y, and the frequency of A is less than or equal to the frequency of B. Okay. Now we know, of course, since the lemma says x and y are the ones with the least frequencies, we know that x dot freq is going to be less than or equal to A dot freq. Similarly, y dot freq is going to be less than or equal to B dot freq. Okay. So based on this, let us try to find the difference between the cost of our original tree and the cost of our intermediate tree, the tree we're going to get after switching x and a. What is the difference? Okay, so by definition, bt is the sum of all the characters in t times their depth in t. Okay, the depth of each character in t times its frequency will give us the cost of bt. Similarly, the cost of bt prime will be the frequency of each character c times its depth in t prime. All right? Now, if you notice, let's go back briefly to the diagram. If you notice, between these two trees, t and t prime, all other characters are the same in terms of their position, except a and x. So a is here, and in its place we now have x. Okay, x was here, in its place we now have b. Therefore, if you are subtracting the cost of this tree, rather this tree from this one, the only element that you really need to worry about is the original cost of x and a, and the new cost of a and x in the new tree. The others will cancel out since they remain in the same position. All other characters remain in the same position. The only one changing are the x, which has now moved to here, and the a, which has now moved to here. Okay, so based on that, we can simplify our summation here by simply concentrating on those characters. So the difference is going to be the cost of x in the original tree, which is x dot freq times its frequency in the tree t, plus the cost of a in the original tree times its frequency, minus the new cost of x in the new tree. Okay, so which will be the frequency of x times its depth in the new tree t prime, minus the cost of a in the new tree times its frequency. All right, I hope this is clear, because all other characters remain the same in their location. So instead of considering the whole tree, this equation reduces to the one that concentrates on just the new values of the cost of x and a in the original tree minus the cost in the new tree. All right, but again, if you look at those three again, the two trees, the first one and the one in the intermediate. Okay, so the position of x in the original tree is the same as the position of a in the original tree, and similarly the position of a in the new tree is the same as the position of x in the all tree. So instead of having an expression that involves the position of both trees, we can make it into an equation that involves the position of just the first tree, the original tree. Okay, again, just to emphasize this point, if you look, the position of x in the new tree is the same as the position of a in the old tree. And the position of a in the old tree, rather in the new tree, is the same as the position of the x in the old tree. So we can replace, therefore, this position or the cost of x or the position of x with the position of a. Okay, and similarly we can replace the position of a in the new tree with the position of x in the old tree. That is just what we have just done. Okay, because what? Because doing this will allow us to actually do some factorization, because we now have two elements with the depth of a in T, this term and this term, and also two elements with the depth of x in the all tree, dt of x and dt of x. So if we factor this out, this is what we're going to have. Okay, so you can see dta is being factored here, so we are left with a dot freq minus x dot freq. Okay, plus similarly if you factor this 2, here you'll be left with x dot freq minus a dot freq. All right, now again, if you look further, these two terms in square bracket are very similar. This is a dot freq minus x dot freq, whereas this is x dot freq minus a dot freq. Can we try and make them to be exactly the same? We can. If we factor out minus 1 from this one, we will have, instead of plus here, we have minus, and therefore this changes to plus, so we have a dot freq, and this changes to minus, we have x dot freq. Okay, now these two terms are exactly the same, so again they can be factored out, so that you will be left with depth of a in T minus depth of x in T. In other words, we're going to have these two terms, these two products. Okay, we can factor out these slack terms. Good. Now we're going to claim that the product of these two is going to be greater or equal to 0. Why is that? Okay, first reason, this term is positive. Actually, both terms are positive. That's why if you multiply them, you will never get negative. So this term is positive because we are told x and y are the elements in our alphabet with the least frequency. So if you subtract a smaller frequency from a bigger frequency, definitely you're going to get positive. Okay, so this is why this term is positive. A smaller value minus a possibly bigger value will give you a positive value, or 0 if they are equal. Similarly here, this term is going to be positive because if you remember, our tree T has A in the deepest position. X was somewhere up. Okay, so the depth of A is higher than the depth of X. So if you subtract, you're going to get a non-negative value. Okay, so that's what we are saying here, non-negative value, because A is at the maximum depth. Okay, if you go and look at that tree T, you see that A was down and X was up. So these two terms are both positive, therefore you're going to get a positive result if you multiply them out. Okay, so what does this mean? If we subtract the cost of our new tree from the cost of BT, we're going to get greater or equal to 0. What does that mean? Given that BT is minimum. Now remember, T is assumed to be optimal. So we now find the T prime, its cost is supposed to be more if it is not optimal. So if you subtract something more from something less, you should get negative, but we are not getting negative. Okay, we are getting 0 or more. Basically what it means is that, in fact, this is not greater than or is actually equal. So basically we are saying T prime is at least as good as T. T prime is at least as good as T. Because if we subtract its cost from the cost of T, we're not going to get a negative number. It's either 0 or a positive number. So our modified tree T prime is at least as good as the original. But T is optimal, and therefore T prime must also be optimal too, since it is as good as T. All right? Therefore, moving X or switching X from where it was to the bottom will yield an optimal solution, as we just did. Now, you can follow the same argument to switch Y and B, and you again will have another tree that is optimal. Okay, so that's what we are saying here. Similar argument can be made for Y, switching it with B. And therefore, it proves the lemma that if X and Y have the least frequencies, we will definitely have an optimal tree where they are the deepest siblings. Okay, so that is basically the proof of the lemma. The second lemma is about proving the optimal substructure. So it's a little long here, the statement of the lemma, but I will show you a diagram here that simplifies what it is actually mean. Let's go through the statement of the lemma. I say let C be a given alphabet with frequency C dot freq defined for each character in the alphabet. Okay, so we have an alphabet, and each character in the alphabet has a frequency called C dot freq. Okay, let X and Y be two characters in C with the minimum frequency. So we're going to assume X and Y are the deepest. X and Y are the deepest, as you can see here. Now let C prime be the alphabet C with the characters X and Y removed and replaced with a new character Z, such that C prime is equal to C minus X and Y union Z. So the only thing here is we are going to assume, so we're going to remove X and Y and replace it with a leaf node Z. Okay, now that Z is going to have a frequency to be the frequency of the sum of the frequencies of X and Y. Okay, so it says here define F for C prime as in C, meaning the frequencies of the characters in C prime are the same as those in C, except that the frequency of our newly added character Z is going to be the sum of the frequencies of the two characters that we removed, okay, X and Y. Now let T prime be any tree representing an optimal prefix for the alphabet C prime. So we're going to assume this T prime which is representing the alphabet C prime, is optimal. Suppose this is optimal. Then the tree T obtained from T prime by replacing the leaf node Z with an internal node that has X and Y as children also represent an optimal prefix for the alphabet C. In other words, if this is optimal, so is this. Basically, what we are trying to prove is that if the sub-problem, because you can consider this as sub-problem because it will have n-1 characters, this will have n characters, so just replacing this 2 by 1. So if a sub-problem is optimal, and we're able to prove that using it, the main problem is also optimal, it means our Huffman coding algorithm has optimal substructure. This is basically the idea. So we're going to assume this is optimal and try to prove that this is optimal as well. All right, let's try to do that. So the first thing we do is to show how to express the cost of BT, the cost of the bigger tree, in terms of the cost of BT prime, the cost of the smaller tree. We observe that for each character in C, rather in C minus XY, okay, so the original tree, the original alphabet, but we only subtract X and Y. Okay, we will see that the depth of each of those characters is the same as in T as it was in T prime. There is no change. The only difference is with the X and Y. So all other characters other than X and Y will have the same depth in both trees. This is what we are saying. Okay. Similarly, therefore, if based on this, if you multiply with their frequency, they will have the same cost. Okay, so C.freq times its depths in T will be the same as C.freq times its depths in T prime. Okay, all other characters except X and Y, because they will be in the same position in both trees. Okay, the second point to note is the depth of X and the depth of Y are equal because they are siblings in the depths in the deepest level, and it is equal to the depth of Z plus 1 because the Z is just one level above. So if you add 1 to the depth of Z in T prime, you will be getting the depth of Y and also the depth of X. Okay, so this will be useful in the following, but we can clearly observe this fact. So now we can therefore say the cost of T, the bigger tree, okay, is going to be the cost of the smaller tree minus Z, the cost of Z, okay, because we don't have Z in the original tree. So we replace Z with the cost of X and Y. So plus the cost of X, obviously in the original tree, will be its depth times its frequency. Similarly, the cost of Y will be its depth plus its frequency. Okay. Now, from what we have just seen here, we can replace both dt of X and dt of Y with this. Okay. So instead of dt of X, we're going to have dt of Z plus 1. Similarly, instead of dt of Y, we're going to replace it with dt of Z plus 1. Z.freq we know is equal to Y.freq, X.freq plus Y.freq. Okay, the frequency of Z is simply the sum of the frequencies of X and Y. Right? So that's what we have done here. I should have colored it to make it clearer. Okay. Now here, what we have done is just factoring out, because both of them has the depth of Z plus 1 as a factor. So if you factor it out, we will be left with x dot freq plus y dot freq. All right. Now, if you notice, we have minus x dot freq. Well, let us expand this one because this is plus 1. If you expand it, you will have this times 1, okay, and this times depth of z in t prime. Now, this x dot freq plus y dot freq times depth of z in t prime, here we are plusing it, here we are minusing it. Therefore, it will cancel out. So what we will be left with is just this term times 1. X dot freq plus y dot freq times 1. So we will have plus x dot freq plus y dot freq. And this is the point we are trying to achieve, representing the cost of BT, the bigger tree, in terms of the cost of BT prime, the smaller tree. So actually the cost of the bigger tree is the cost of the smaller tree plus the frequency of x plus the frequency of y. This is what this shows. Equivalently, we can say therefore the cost of the smaller tree BT prime will be equal to BT, the cost of the bigger tree, minus x dot freq minus y dot freq. Okay, let's take note of this. We're going to need it in the next slide. Okay, so if we have those two trees represented as they were, a bigger tree with x and y, and a smaller tree where x and y are replaced with a leaf node having the sum of the frequencies of the x and y, then this will be the relationship between their two costs. Okay, this is the first step. The second step in the algorithm is to try and now prove the lemma by contradiction. The lemma, if you remember, is trying to say if the smaller tree is optimal, so also is the bigger tree. This is what we're going to try and prove next. So we want to prove it by contradiction. So suppose that t does not represent an optimal prefix. Okay, we are trying to show that t is optimal. So we are now saying suppose it is not. And if this leads to a contradiction, it means that actually t is optimal. Okay, so suppose t does not represent an optimal prefix code for C. Then there exists an optimal tree T double prime whose cost will be less than that of BT. Okay, if T is not optimal, then we're going to have another tree which is optimal, and because it is optimal, its cost is going to be less than that of T. Okay, now by lemma A, the one we proved earlier, which says if you have an optimal tree, then the two elements with the least frequency, you will find them in the deepest level, right? So by lemma A, T double prime, which is optimal, will have x and y as siblings in its deepest level. All right, I'll show you that again in this diagram. So T is optimal, therefore by our lemma, it will have this x and y. Remember, x and y has the least frequency. So by lemma A, we should be able to find them in the deepest level of our optimal tree here. Okay. Now let T triple prime be the same tree T prime, but with the common parent of x and y replaced by a new node z, whose frequency is the sum of the frequencies of x and y. Okay, So let us obtain another tree by replacing this node, which is a leaf node, Z, whose frequency is the sum of frequency of X and Y. Essentially what we are saying is T double prime and T double prime will have this similar relationship than the one we saw in lemma A. Okay, and we know what we obtained from the last slide. If you have such a situation, then the cost of the smaller tree, so the cost of 3 triple prime is going to be the cost of the bigger one minus the frequency of X minus the frequency of Y. Okay, this is from the last slide. We just obtained this relationship. All right, but remember, BT prime is optimal. All right, this is the assumption. Suppose there exists an optimal tree T double prime. Therefore, if you replace the cost of that optimal with the cost of our T, the T that we are trying to prove that it is indeed optimal, although we say it is not optimal here, we suppose it is not optimal, we should have a bigger cost. Okay, if we replace a smaller value with bigger value, we should get something greater, right? So this is greater than that, right? Now, this is the issue, because from what we proved in the last slide, this is actually BT prime. BT minus freq of X minus freq of Y is actually the cost of T prime. And this is the problem, because we are now able to find a tree, okay, whose cost is less than BT prime, okay, where BT prime, we assume it to be the optimal, remember? So therefore, there is a contradiction. Okay, this B triple prime cannot be less than BT prime, because BT prime, if you remember from the beginning, was optimal. So we have a tree whose cost is less than BT prime. And this is basically a contradiction. All right, the contradiction was because of our proposal here. We say suppose T does not represent an optimal prefix code. If we do that, this is what we are able to get. We got another tree whose cost is smaller than the optimal tree. That is not going to be possible. So what this means is that actually T is optimal. Okay, this is the proof by contradiction. So therefore, this proves that the Huffman algorithm actually has an optimal substructure property. Okay, if this is optimal, then so is this. This is what we have just proved. And therefore, greedy algorithm in fact satisfies the optimal substructure property. Now we're going to combine both lemmas into this theorem. And the theorem says Huffman's algorithm produces an optimal prefix code tree. Okay, and this follows directly from lemma A and lemma B. We don't have to do anything else. We have proved that the algorithm satisfies the greedy property, and also it satisfies the optimal substructure property, and therefore that the tree it will give us is indeed going to be optimal. Okay, so this brings us to the end of the second part of the lecture on greedy algorithm. As usual, we have exercises to allow you to practice, especially the Huffman algorithm, how to apply it, to get the tree first, and also how to use the tree for decoding as well as encoding. So exercise number 1. It says, suppose we have information to be transmitted over the internet containing the following characters with their associated frequencies as shown in this table. Okay, so A is 45, E is 65, and so on. So this time the elements are not sorted. You have to make sure you sort them when you are doing the algorithm. Okay, they must be enqueued based on the frequency. So what is the question? Use Huffman code algorithm to answer the following. 1. Build the Huffman code tree for the message. Based on this, what is the Huffman code tree? Alright, so you just go and follow the algorithm exactly like we did. You enqueue in this first into a priority queue, and then you keep dequeuing them and joining to form a tree until you end up with one tree. That tree is the Huffman code tree. Based on the Huffman code tree, you will be able to generate the code words. This is the next part. So use the tree to find the code word for each character. Okay, to find the code word, just follow the tree from the root. If you see that you're going left, you allocate 0. Going right will give you 1 until you reach the character, and the sequence you get will be the code word for that character. Once you have that, now answer the next question. It says, if the data consists only of these characters, what is the total number of bits to be transmitted? Based on the code word that you found here. So we know the length of each code word and we know the frequency. We should be able to find the total number of bits that will be transmitted. Just follow the equation BT equal to summation of the frequencies times the depth of each character in the tree. Okay, and the next question is asking you to compare between what you did here and what will have been sent using ASCII. What is the percentage saving if the data is sent with 8-bit ASCII values? Okay, that is the first question. The second question is saying use the Huffman code tree that you obtained from exercise number 1 to 1. Decode the following sequence of bits. So if you are given this sequence of bits, what do they actually mean in terms of these characters? Okay, this is A. And B, write the bit sequence that will encode each of the following. So now it's the reverse. Instead of giving the sequence of bits, you are now given a sequence of characters. What is the equivalent of these characters in terms of bits? Okay, so those are the exercises, and that brings us to the end of the lecture on greedy algorithm. Thank you very much.